Jumping right into a really fascinating intersection of ambition and engineering today. We're focusing on one machine that has, well, it's captivated and maybe polarized the entire tech world, Tesla's Optimus humanoid robot. And you really can't talk about this robot without mentioning the sheer audacity of its creator. I mean, Elon Musk has declared that Optimus could account for 80% of Tesla's future valuation. We're talking potentially more than $10 trillion. And he's targeting a price point of what, $20,000 to $30,000? Deliberately less than a car. When a claim that big is made, you have to look past the hype and ask, is the engineer actually there to back it up?
And that's the mission for this deep dive. We're moving beyond the sizzle to really understand the stake. To properly evaluate that, $10 trillion vision, we need to unpack three critical areas. First, the specific strategic advantages Tesla has in AI and hardware. Second, we've got to analyze the recent performance milestones, especially this new focus on running speed. That changes the game. And finally, we are diving into the deep science of bipedal control, the really complex theories from ZMP to hybrid aerodynamics that make this kind of agility even possible.
Okay, so let's unpack that strategy first. Tesla isn't just hiring robotics engineers from scratch. They're essentially porting their entire existing AI ecosystem over. They're leveraging the neural nets, the visual processing, and crucially, all that training data from millions of cars running full self-driving.
Right. That fleet-wide learning infrastructure is their immediate non-replicable advantage. I mean, think about it. Most robotics companies spend decades trying to build up enough real-world data to train a vision model. Tesla is starting day one with maybe the most comprehensive perception system out there on consumer hardware, but that only gets you halfway.
So the other half is the hardware. And this is where that vertical integration comes in. They didn't just buy off-the-shelf parts. They built the motors, the structure, the brain. What's the advantage there?
Control and cost. I mean, that's the key if you want to hit that $20,000 price target. They custom designed their own rotary and linear actuators, all using a planetary roller system. This vertical integration means they control the cost, the energy density, and the supply chain from the very beginning.
And the raw power from those actuators is just staggering. We saw demos where a single unit could lift 500 kilograms. That's a concert grand piano.
Yeah.
But I have to ask, does that raw strength really translate into agility, or is that just overkill?
It speaks to the potential. If you want to move fast, you need those powerful bursts of torque. And structurally, they balance this power with lightweight materials, a lot of which they share with their vehicle programs. They even house the 2.3 kilowatt-hour battery, which is designed for a full day's work right in the torso to keep the center of mass really optimal for stability.
And they're not skimping on articulation either. It's got 28 degrees of freedom in the body, plus another 11 per hand. And they're leaning fully into the camera-centric approach, right?
Absolutely. They're sticking to their guns on that. Autopilot-grade cameras for vision, no LiDAR, which is an interesting decision, given how critical LiDAR is in a lot of other industrial robotics. But for fine detail, they've integrated these custom tactile sensors using metallic tendons right into the fingertips, so you get that complex manipulation feedback.
So you have specialized, powerful, vertically integrated hardware, and it's all managed by a modified FSD software stack. And that's all running on a single Tesla system on chip, a central brain handling vision, planning, control, everything with these end-to-end neural networks.
And that software synergy is the key to improvement. It's all continuous improvement through reinforcement learning. The whole system is designed for fleet-wide data sharing, so every time one Optimus learns to walk over a new cable or handle a tricky part, that data feeds back to the central network and improves every other unit. They're basically crowdsourcing natural movement by mapping human motion data onto the robot's own body.
The scale of the ambition is it's breathtaking. We're talking production starting at 5,000 to 10,000 units in 2025, maybe 50,000 by 2026. And the vision is massive. Factory work, chores, elder care, and then the really ambitious plan, sending Optimus to Mars on a Starship in 2026.
Okay, let's pivot hard to performance, because all the strategy in the world means nothing if the robot can't actually move. And that recent video showing Optimus running, untethered, that fundamentally changed the conversation about its maturity.
That video was a critical technical marker, a huge one, because it demonstrated a true flight phase. When both feet are off the ground at the same time, you're technically running, not just walking fast. And that signifies a leap into the realm of dynamic instability. The robot is actively falling forward and constantly catching itself. It demands incredibly complex, high-frequency control. The community immediately got out the stopwatches and measuring tapes for that one. What was the verdict? What was the speed?
So based on independent analysis of the footage, using background objects for scale, the consensus estimate puts Optimus's speed at about 3.8 meters per second.
3.8 meters per second. That's around 8.5 miles per hour.
Yeah, exactly. Which is a really significant PR for a full humanoid platform.
And that number puts Optimus squarely in the high-performance tier, doesn't it? How does that 3.8 stack up against the other top bipedal platforms we know?
It's highly competitive. You've got the Unitree H1 at 3.3 meters per second. Robotera's Star 1 was verified hitting 3.6, though they claim their newer L7 model can reach 4.0. And then, of course, there's Agility Robotics Cassie, which is just a leg platform, but it holds the record at 4.0 meters per second.
Wait, okay. You mentioned Cassie is a leg-only platform. Optimus is a full humanoid. Arms, a torso, all that extra weight. Is 3.8 on a full humanoid really comparable to Cassie's record? Or are we sort of comparing apples and oranges here?
That's a crucial distinction to make. Optimus has 28 degrees of freedom just in the body, plus all the weight and inertia of that upper mass. Cassie is pure running machine. So achieving 3.8 with a full upper body is a huge accomplishment. But, we have to inject the standard caveat here. This PR was set in a controlled lab environment, flat, high-friction surface, and that environment simplifies the control problem immensely compared to, say, a messy factory floor or the Martian desert.
Right, so we know the motors are powerful, the running speed is impressive, but this kind of dynamic agility, it requires more than just raw power. It's about mastering controlled falling. And that brings us to the deep science that makes it all possible. Why is high-speed bipedal movement so fundamentally difficult?
It's the constant fight against gravity while maintaining your momentum. Historically, robots relied on techniques that focused on static stability. The poster child for this was the zero moment point, or ZMP, criterion. That's what platforms like Honda's Asimo used.
ZMP sounds wonderfully safe. But if you're trying to sprint, safe just means slow. So how did the field finally escape the tyranny of, perfect static balance?
Well, ZMP is conservative. It requires the center of pressure, the total of all your ground forces, to stay strictly within the area of your foot on the ground. You're always balanced. You're always within that support polygon.
You can't fall.
Right. To get speed, the field had to shift to dynamic models. And the most famous of these was the spring-loaded inverted pendulum, or SL8 model.
The SL8 model.
Right.
That showed that dynamic locomotion wasn't about staying balanced, but about controlled, repeating instability. A stable periodic orbit.
Precisely. It's controlled falling. The SLEAP model demonstrated that by properly timing your push-off and your flight phase, you could get this highly efficient locomotion. And that's really what inspired the fundamental design of robots like Cassie.
But when you graduate from just two legs to a full-bodied machine like Optimus, you have to deal with the full complexity. You have a system where continuous movement, like a leg swinging, meets these discrete dynamics, like a foot hitting the ground. That's where the advanced theory comes in.
It does. We're talking about what are called hybrid systems. These are models that account for both the continuous and the discrete dynamics, and the theoretical core that enables dynamic stability in machines like DRUS and Cassie, and certainly what's underlying Optimus is called hybrid zero dynamics, HZD.
Okay, HZD, that sounds incredibly intense. Give us the analogy. How does HZD work to tame such a complex machine?
Yeah. Okay. Think of HCD as imposing a kind of mathematical harness or a guide rail onto the robot. You start with this extremely complex robot model, hundreds of variables. HCD uses this sophisticated nonlinear feedback control to impose what are called virtual constraints. These are basically rules the controller has to follow, like the ankle must always relate to the knee angle in this very specific way.
So it's simplifying the problem.
Exactly. By forcing the robot to satisfy these virtual constraints, the full, complex dynamics of the robot are mathematically collapsed down onto a simpler, lower-dimensional space, and the space is called a zero-dynamic surface. If the robot stays on this surface, we have formal mathematical guarantees that its motion, even after a sudden foot strike, will be stable. It's like the mathematical highway that ensures a stable, repeating gait.
So the complexity isn't about teaching it every single micro movement. It's about forcing the entire system onto a stable mathematical pathway.
Okay.
So if HZD gives us the stable framework, how does the robot decide which specific path, which gate is the most efficient one to take? That's where optimization comes in, I assume.
That's where closed-loop optimization, often using something called nonlinear programming, or NLP, becomes essential. We don't just hand-tune a gate anymore. The robot's trajectory parameters, which are defined by those HCD virtual constraints, are optimized over a step cycle to achieve specific high-level objectives.
And those objectives usually revolve around efficiency, right? You want speed, but you don't want to burn through your battery in 10 minutes.
Exactly. The primary objective is often minimizing something called the mechanical cost of transport, MCOT. MCOT is basically the robot's miles per gallon. It measures how much mechanical energy the robot burns to move a pound of itself 1 foot forward. So we optimize to reduce that MCOT while simultaneously satisfying every physical reality check. You have to stay within friction limits, respect the maximum torque of the actuators, and, crucially, maintain that HZD stability condition.
That sounds like a massive calculation to be doing on the fly. And speaking of high-frequency control, that brings us to the tool that keeps us all from going sideways. Control Lyapunov functions quadratic programs, CLF-QP.
It's a mathematical mouthful, but it's one of the most powerful real-time tools in modern robotics. Think of CLF-QP like the high-speed stability control system in a Formula One car. A control Lyapunov function, the CLF part, is a mathematical guarantee that the robot state will converge exponentially toward the desired motion. Basically, it will stay stable.
Okay. And the controller uses a quadratic program, the QP, which is an optimization problem it can solve almost instantaneously. It selects the motor torques that satisfy that stability guarantee while also respecting all the physical constraints, like torque limits. And this entire process happens at incredibly high frequencies. Some of these implementations operate at 5 kilohertz. To put 5 kilohertz in context for you, that's 5,000 stability checks every single second. Your fastest possible voluntary human reaction time is maybe 5 checks per second. This is machine reaction speed, constantly prioritizing stability above all else.
And that high-frequency loop is precisely what allowed Agility Robotics to push Cassie to its absolute limits and set that Guinness World Record for the 100-meter dash. That achievement was the ultimate validation of this whole optimized control theory in practice.
So what did the analysis of Cassie's record run tell us about these optimized gates? Did it reveal anything unexpected about the physics of bipedal running?
It did. It revealed that the optimization favored efficiency and speed over, well, what might feel comfortable to a human. The most efficient, highest-speed gate relied on taking these long, infrequent steps. It was characterized by a high swing ratio and a really significant aerial or flight phase. The robot was airborne for a surprisingly long time during each step.
So the math confirmed that the most efficient way to run is to push off hard and fly as far as you can.
And that optimized behavior showed really strong qualitative similarities to human runners, specifically similar stride length and frequency curves as a function of speed, which demonstrated that the optimized robotic gait is genuinely closer to natural human running than the older, manually tuned gaits were. However, and this is a crucial insight, the study also found a limit. It found that Cassie's maximum performance wasn't limited by the computational power or the stability theory, it was limited by the hardware. Specifically, the hip roll motors were hitting their maximum torque above 3 meters per second, and that motor limitation prevented the robot from generating the higher ground reaction forces it needed to go even faster. Unlike human runners, who just keep increasing that force linearly with speed.
The age-old battle, huh? Software potential being constrained by hardware reality. But despite those limits, the final figures are still powerful. Cassie achieved a world record time of 26.11 seconds for the 100-meter dash. That's an average speed of over 4 meters per second. And this wasn't just a running start. The rules required a standing start and a controlled, stable stop at the end, which means the control system had to precisely manage the transition between two completely different control policies, a static standing policy and a dynamic running one.
And those transitions are extraordinarily difficult. For the start, they had to time the exact moment to swap policies for maximum efficiency. For the stop, they had to wait for the foot to be at its highest point to give the standing policy the best possible chance to plant a wide stabilizing base before it could take over. It's all choreography measured in milliseconds.
So wrapping up this deep dive, the key takeaway for you is this. When you see Optimus or Cassie hitting these incredible speeds, you're not just seeing a strong motor. You're witnessing the successful real-world transition of these sophisticated control theories. Hybrid zero dynamics, gate optimization, real-time CLF-QP moving dynamic machines beyond static stability and into true agility.
Absolutely. The impressive speeds and stable, periodic gates walking, running, they're being mastered now in controlled environments. But the long-term challenge, the future of this field, is achieving full autonomy in unstructured environments and developing controllers that are capable of a periodic dynamic motions, the ability to jump, pivot, trip, and recover spontaneously. That's the real frontier for deployment in factories, homes, and, yeah, even on the surface of Mars.
And here is a final provocative thought for you to mull over. If the current control systems are so precise that maximum speed is limited by something as specific as the torque in the hip roll motors, and if simple transitions like starting and stopping require such specialized, precisely timed policies to avoid failure, what fundamental breakthroughs in either hardware design or maybe generalized AI learning have to occur before these machines can truly navigate the messy, unpredictable reality of a cluttered home with the same casual, confident agility we saw in that pristine lab demo?
That is the $10 trillion question, isn't it?
Indeed. We've reached the end of this deep dive. We'll talk to you next time.